Engineering Eng. PDF document of this video is on engineering.com.
Hello friends again. I tried to briefly explain the Cartesian coordinate system in our previous video. Now let's move on to cylindrical coordinates if you wish. We will look at DL, DS and DV software in cylindrical coordinates. Elements of cylindrical coordinates are ρ, phi and z. Let's examine our coordinate system as follows. What do we mean? Now we have x, y and z observation point as usual. And in our previous video we just tried to define it with x, y and z vectors. So they are length vectors after all. Now we will look at how we define it in terms of ρ, phi and z. First of all, we will say here, how do we define our small r length? Let us state this. Let's take the xy plane first. Imagine writing the xy plane again this figure. I just took the xy plane, so I reduced it from 3 dimensions to 2 dimensions now. Then I projected this observation point P on the xy plane and I called it P prime. P prime point projected on this xy plane now is a place like this after all. Then I say from here xy origin to P prime point, that is, I moved the P prime point here, so I took it directly to the xy plane in this plane. Here I say that the length that rotates in the xy plane is ρ, and the angle this makes to x is called phi. We need to know this first. Then we have to define this here. We know that again, right? I have a certain length x in the rx direction, ex in the x direction, y size ey direction, z magnitude ez direction. I called them x0, y0 and z0 in the previous video. It doesn't matter. So here I think of this as magnitude and this as the direction where the relevant magnitude is. Now this is what looks like a Cartesian here. Look here, it's look like a Cartesian. Let's see how we are going to make it cylinder. How do we do it cylindrical? I'm focusing on it now. Look, I see an x here, right here, where I have the place representing x here. See, when I get down there perpendicular to this is x. The length that this represents x is the length of here that represents y when I get down. Now I ask you, you see a right triangle has formed here. How would I express x if it is a right triangle whose hypotenuse is ρ? I write ρ cos phi as neighbors here. I write ρ sin phi for y the same way. So if I want to rewrite r now, can I write this instead of x? ρ cos phi ex direction, ρ sin phi ey direction. There is no change for z because z is already an element of this coordinate system. So I write it as z ez. Why did I change this here? When you look at it, because there is nothing in terms of x and y here. If you pay attention to my x and y, how did I express it? I express x in terms of ρ and phi, which are the new elements of this coordinate system. See here, ρ and phi, no x size ρ and phi left. Likewise, since there is no such things as y here, I also have to express it in terms of ρ and phi and expressed it as ρ sin phi. Now, after I have expressed in this way here, an important point for me is that, guys, Of course, I will have to write a DL for them too. Like, how do I rewrite DL for rho? How do I rewrite DL for phi? How do I write DL for Z? First of all, you already know that the length is no different from the previous one, dz in direction of Ez. We have no doubt about that. But there is a situation like this. I did not give it because we did not need to write all of them in the previous Cartesian, which we call matrix. But I say this as this is the point where the subject is more important. These are normally written as h rho, e rho, t rho, and here as h phi, d phi in the direction of e phi. So, how do I find h rho and h phi here? Likewise, I have to say that dlz is actually in the form of hz, ez, and dz, but since the matrix of the lengths are 1, I did not need to mention the matrix here. Now let's talk about the matrix. Let's see how we can find out how it's made in metric. The formula for what we call a metric is, for example, if I want to h phi, I find its magnitude, r vector, its derivative according to right direction vector, and find its magnitude. How do we do this? See, if we found r here, right, r is here, then what I am doing? Take the derivative of r with respect to phi. Then what do I find here first? I have to find the derivative of r with respect to phi. First, I find it. Then I will take its size. See, now what is the derivative of this with respect to phi? The derivative of cos is minus rho sin phi ex. Rho sin phi, what is that? Let's delete this x. What is the derivative of the sin? Cos. Then rho cos phi ey. What is the derivative of z ez to phi, guys? Is there anything connected to any phi here, or I can automatically write 0 ez or 0? But here it's always useful to protect this setup, so it's our benefit to protect the vectors. So now, what does he want me to find here? Its size. How would the size be found? If you remember, I gave a feature like this in the first video. If I wanted to find the size of A, I would multiply A within itself and take it into the root. Then what should I do? What will happen if I multiply by itself? Let's do it like this, and I will say A here. If I do A times A to find it and put in the square root, I find its magnitude. Imagine that I multiply this by itself. At this point, we need to know that the mutual products come in, guys. So when I multiply this with this, imagine that I multiply minus rho sin phi ex plus rho cos phi ey plus 0 ez by itself. It's going to be ex times ex1, and the product of the differences is 0, guys, right? This is the case in scalar. So using this property, I multiply the length and enclose the square root. Can we see that Rho times rho squared sin squared phi plus rho squared cos squared phi plus 0 will come. I am reorganizing it now here. My goal is to find h phi. H phi equals the magnitude derivative of r with respect to phi, and I multiply the solution of this in the square root. Rho squared sin squared phi plus rho squared phi cos squared phi next. If I put this in the square brackets rho, here is sin squared phi plus cos squared phi. What is this, friends? So what we find h phi with root rho square root if this goes. H phi rho remains. In this way, I found the metric here. Then I can write the h phi here rho then this way. I delete that after finding that h phi is rho. When I found h phi is equal to rho. If I want h phi rho, what I write dl phi, the corresponding direction vector was h phi d phi in the direction of e phi. Then I write in the direction of e phi, h phi, rho dl phi, friends. Likewise, if you want, let's rewrite dr, or rather let's rewrite r here. Rho cos phi ex plus rho sin phi ay plus z ez. I am going to try to prove that here. Let's prove that the metrics of the length are 1. We do it like this. Let's write it in this corner. Let's show 1 or not. As follows, I say h rho equals magnitude dr divided by the relevant derivative. Considering that we take a derivative with respect to rho, can we write as follows: dr over d rho equals cos phi ex plus sin phi ey z no rho 0 ez. It says take the size of it. What I am doing then, if I take square of this and enclose in the root, I find h rho. Let's do it again. Multiply this is by itself. It says to me if I multiply it by itself, those in the same direction will get ex times ey0. All I need is the part here that ex times ex. So what will come from here? Let's write here again. I'll find dl divided by d rho in magnitude like this. Cos squared phi plus sine squared phi will come in the root. This is already equal to 1, friends, which is equal to h rho. Imagine that we are doing the same for speed as by derivative the magnitude of hz in the relevant direction and finding its magnitude. Likewise, that the derivative of r with respect to z. There is no z here. So 0 times ex, 0 times ey, the derivative with respect to z 1 times ez. Therefore, when you look here, I find the size of this again. When I take the square of it and take into the root, what will I find? 1 times 1 into root of 1 squared it equals speed. That room equals 1 again, friends. I was expecting it to come out again because speed that is a length. In summary, we can say that the matrix of the lengths are 1 and the rest give a different result. In summary,
h rho and hz is equal 1 and hv is equal rho.
after that, let's move on to ds writing. Imagine that I wrote for rho and phi in the same way in ds spelling here too. This drawing is also important, which is the direction vector. Just as we did it for ex, ey, and ez, it will be a plus for rho, phi, and z when going this way, guys. Minus for the rest. When I think accordingly, rho and non-phi, whichever is in that direction, ez, then in the direction of ez. When I go from rho to phi, I look clockwise or not, because it's clockwise plus ez. We write the matrix first, friends. H rho, the matrix of this, h phi, the matrix of this, then d rho d phi. Now I say it equals again plus e was 1 of the length of h rho in the direction of z, across, because it was h phi rho. I write it exactly like this again, because it was h phi rho. I write it exactly like this again, and so this was equal to ez rho d phi, friends. ds rho and phi. Let's write one more example now. The one for ds, z, and phi. When you look which one is not in the direction of rho, because I go counterclockwise while going from z to phi, which is not minus, there is z there, phi, no rho, so their matrix are hz, h phi, and their dl, daz, and d phi. If we arrange this in the direction of minus e rho, h phi, rho dz, d phi, as a result, I have a matrix of size rho in the direction of e rho, so I get dz z phi in the form of dz d phi. Finally, let's write the volumetric dimension. For volumetric again, I write the product of the three-dimensional direction vectors for dv. For this reason, I do not find any direction vector, a vectorial result for dv, but I have to write all the matrix h rho, h phi times d rho, d phi, and dz. Then dv, what happens, guys? H rho, h phi rho, hz, d rho, d phi, dz. So what happens as a result? dv for rho phi z. Rho times d rho, d phi, and dz this way. We made these definitions for cylindrical coordinates. In our next video, we will examine the global coordinates. Bye now.